and share my screen. Okay, can anyone see the paper? I shared my screen, but it doesn't indicate to me that.
Yep, it seems fine.
Okay, cool. Hey everyone, welcome to NPLAN's Paper Club. Today I will be presenting this paper called Zero Shot Causal Learning. And just to break apart some of the terminology there. So there's two concepts in the title. One being causal learning, which is when you estimate the impact of like an intervention, or you estimate, it's like you're given a system and the system has some description and you intervene on the system, you change something or you add something and you want to see what impact it will have. I think that's a poor explanation of causal learning in a nutshell. Hopefully going through the paper, we can get to a better one. And zero shot means that you are given a new system and you have to figure out what the impact of the intervention or the changes that you perform without having seen that system before, or that the change that you're going. In this case, it's actually without having seen the change that you were actually both. So both the system and the change that you're going to perform on the system. Those are, I think, well, as we go through it, it will become more obvious, and we'll be able to. You can use more concrete. I'll start using a concrete example to explain it, but I wanted to go over some like basic variables, and then get like an example to explain those variables. So where is it? Okay, you can use that. Okay, so there's essentially three components to a causal learning problem. You have X, which I call the system. You have X, which I call the system. And usually when you're talking about causal learning problems, the first place where they were applied was in the setting of estimating the impact of medicines and different treatment options for patients. So X you could think of as a person, and that's why the diagram that we're looking at here has a person. So it's a description of the person with some type of numerical features, or maybe like an embedding, of the of some text description of that person. And then you have W, which is the treatment, the intervention, the change to the system. So that can be like you introduce a drug, or you change the diet of the person, or something else that would affect their health. And then Y is the impact of that intervention on that person. So maybe you have a person who has a headache, and you have a new medicine that you want to use to reduce the symptoms of a headache. So you give them the medicine, and the impact is whether they felt less like the headache had gone away or not within a couple hours. So yeah, you have these three variables, X, W, and Y. Now, in the zero shot case, what they're saying is that we have a data set of, and I guess we'll introduce this. Where is it? Okay. Wait, no. So you have a data set of triplets, which is a description of a person, the treatment that they were given, and then the impact of the treatment, Y. And you have a data set in this case of not a single treatment, like a single drug being administered, but many different drugs being administered. But all of them are being used to to evaluate like the same, whether all of them are being used to perform the same treatment or have the same effect. Like you're evaluating the same effect on all of them, and you want to train a model to estimate for each individual, like if you get a new patient, what the impact will be. The reason why I'm describing all of this is because I wanted to introduce what I think would actually be the most naive baseline to this problem, before going into the methodology here and kind of going into, I actually am going to go into the introduction after this, but I wanted to introduce the most naive baseline, so I think you can have it in your head, and then yeah, I think it's a bit helpful because one of the questions I had when I was thinking about this paper was like, how does this differ from like a really simple approach? Sorry, there's someone I need to add. So basically, I think the simplest approach to this problem would be that you have some feature vector X for each individual. For each data point in your data set, you have some treatment vector X. You have some treatment, some patient vector X or some individual vector X, and then you have some treatment description vector, because they have that as well. And that's a key component of this method. And then I think the simplest method would just be separating your data set into training, validation, and test set, where your test set would have different treatments than your validation and training set, which is the key idea that they have. But then you just train it in a supervised manner. So you have some model that concatenates the two vectors, the treatment vector and the patient vector, and then you feed it through the model and it gives you a distribution over outcome. And you just train that in a supervised manner. I actually would have liked to see that as a baseline for this paper, just because they do something more complicated here. And it would be interesting, in my opinion, to see what the most simple baseline would do. I hope that makes sense, but let's go through it now that I've introduced this idea. So the whole point of the paper is that we want to be able to estimate at an individual level the impact of interventions, because it's a lot easier when you're trying to, you have a specific treatment. It could be another example of where you can apply causal learning is in trying to estimate the effect of policies. So for example, providing providing school vouchers to students so that they can go to schools outside of their where they live into other parts of like a city or an area. You would want to estimate the average treatment effect. So like, how does that impact education as a whole? That would be an average treatment effect. But what if you want to estimate on an individual level the impact of giving school vouchers so you can like maximize the impact overall of what you're doing? So being able to estimate the impact of an intervention or like a policy or a drug is very useful. But it's actually a very hard problem. And the authors of this paper, they are introducing or proposing a causal meta-learning framework to estimate the personalized effect. And they're making it an even harder problem by saying that, you know, we have this, we're assuming we have some data set of interventions and we want to train on a different set of interventions than we test on. So essentially we want to train a model to estimate the impact of interventions, but the set of interventions we're going to test on, it's never seen before, and it has to correctly estimate how those are going to impact the individual. And so, yeah, they're using a causal meta-learning framework. There's a lot of details there. Besides the method that they're proposing and some proofs related to it, they show that experimental results on real-world data sets and large-scale medical claims and cell perturbation settings demonstrate the effectiveness of our approach. And most strikingly, their approach outperforms strong baselines, like ones that are only have to estimate the impact of a single intervention. It's the intervention that it's being tested on. So I guess that kind of demonstrates that there's a lot of shared structure between these tasks, and that you can take advantage of that shared structure using a method like CAMEL. I'm sure there's another paper that has CAMEL as an acronym. That's just a random thought. Let's see, is there anything over here? They do talk a little bit about the impact of this work, and I do think it's worth noting because zero-shot causal learning could have like, as I say, could revolutionize healthcare by enabling personalized treatment for each patient. And the reason is because often patients are given completely new treatments with respect to everything that's been done before, or what's the other example they give? Or when a new drug is put onto the market, it's being you want to give patients information or doctors information about what impact it could have, and then you need to do zero-shot causal learning as well. So there's a lot of areas, especially with health, where being able to do this effectively would be really beneficial to society. So from that perspective, it is actually a really good problem to work on. So good motivation there. And they do introduce.
I was thinking, wouldn't it be more to make research more efficient, right? Because in practice, if you don't know yet what a new treatment is actually going to be like, right? I think that's the whole point of the paper, that you have no experiments made on the drug yet. So the question is the drug likely to be effective?
Yeah, that's also true. That's another positive impact if we can get this. If we can solve this problem, that you can perform research in a much more systematic way, because maybe even if it's if it was perfectly effective, you wouldn't have to do research anymore. But if it wasn't perfectly effective, but pretty effective, then you could probably whittle down the number of the search space for new drugs, or and be able to do it a lot quicker.
Or run studies on a selected subgroup of patients, right?
Yeah.
Of course, that becomes also with ethical background a little bit, right? But could be quite interesting. But of course, if a big pharma company, a lot of money they lose by having trials that end up not being actually effective, right? And if they can save 10% of that money, it's in the millions, right? And
yeah. Although
you would.
Sorry, go ahead.
No, I was just saying, but if you then say choose the patients to be likely benefiting most, you potentially also shifting the whole problem, and at some point, of course, causal inference breaks down if you were to keep doing this, because it sort of has this assumption built in that it's sort of random how you assign treatments, which would stop at the first iteration essentially. Sorry, I was rambling.
That's what I was gonna say. Like, there's a lot of different parts of like assumptions that you make to make the math work for causal learning, where you assume, for example, that every single treatment has a non-zero probability of being applied. Is one of the major assumptions, which we'll go over in a bit.
Yeah, and there being no hidden confounders as well, right? So it's essentially saying that the data you have is, for your intents and purposes, already good enough, which in reality is probably not quite correct.
Yeah.
Sorry, go on, please.
I was just gonna say two things. As we go through the paper, I think I'm just gonna try to introduce some of like the key concepts, because I think there's a lot to break down here, and what I consider fundamental concepts. So, but before I introduce the first fundamental concept, I did want to say that Arvid pointed out how this could be really good for drug discovery, but one of the, I think, sadder things that happens in healthcare is that a lot of money goes towards drug discovery and none goes towards estimating like treatment, or even doing research in university on treatments that you can't make money off of. Like, for example, estimating the impact of specific diets on people's health. But this type of methodology could also be used to do that, just because it's not relying as much as normal causal analysis on having like a really well-designed experimental design. You could have like a couple of patients who tried one intervention and a couple of patients who tried another, and you can aggregate over like millions of people to maybe do good health, get good estimates of like the impact of other treatments that are free, like, I don't know, not eating meat. So that could be an interesting element that this paper could maybe make it easier for us to do research into that, or maybe the government can start funding more research into free treatments that help people's health. Anyway, that's more of like a ideological discussion. Sorry for the aside. But they introduce one of the fundamental concepts of causal learning, which, funny enough, they're one of their experimental, like one of their data sets in their experiments breaks. But it says it's that one or more downstream outcomes, Y, are monitored for each individual. So basically, the idea for a lot of this work is that you can only apply a single treatment to an individual. You can either give them the drug or not give them the drug and view the impact. And you can't observe both of those two things. And so at any given time, for the data sets that you're working with, you won't be able to estimate what's called the causal, like the causal treatment effect for an individual, and or the conditional average treatment effect, because you won't be able to see like the difference between what would have happened if you had given the treatment versus what you had not. And that is like one of the issues that's created in causal learning, like by the nature of the problem that you're trying to address with the methods that you use. Yeah. So, okay.
Sorry, can I'm not sure if I can ask a question. Excuse
Yeah.
my ignorance here, but would this also be would this be able to solve an area in medicine to do with personalized medicine? I mean, would this could this be used in that context, or have I just completely got that wrong? Sorry.
No, that's exactly where it would be used. I think in the introduction, that's like one of the main motivations that they use, that you could ideally, if this model is very accurate, you could zero in on which treatment would have the highest impact with respect to not treating the patient for whatever problem that they have.
Okay, thank you.
Okay, and so another element of I'll just go through it one by one. Another element of the problem, like I said before, is that usually when you have you're estimating treatment effect, you only have like an indicator of what treatment was given to the patient. But here you also have some high-level way of describing it, which is this information H. And that's a key component of the method and just the problem when you're trying to do zero-shot intervention. Zero-shot inference is like there has to be some common way of describing all of these, and that there has to be shared information between the different treatments. Otherwise, there's no point. Okay, so let's quickly go through related work. With related work, they say there's not really anything that's close to what they're working on, in the sense that all the other methods that do like this zero-shot prediction are specific estimators. So they claim that their method is model agnostic. You could use any causal average treatment, conditional average treatment effect estimating model with their method, which in theory is true. And you would be able to, and whereas all the other methods that have occurred and have happened in the past use a specific model that they propose. So this is a model agnostic technique, and it can be used with any of the models that have been used in the past. So yeah, that's one of the benefits of this method. Although my impression from the experiments, if I remember them correctly, is they only use a single estimator with their method. So while I think it's a valid claim to make from a theoretical point of view, maybe it would have been good for them to do experiments with other estimators. Although at the same time, you know, at some point you're asking a researcher to do millions of experiments when you go down this route. So I can also understand why they didn't do it. So yeah, that's the main difference. This is a model agnostic method that is, as long as you have a model that could estimate conditional average treatment effect, then you can use it with this method. Okay, and let's go into the background, and this is where I need to be better at my explanation so that we've clearly described the problem. So they say we first consider the problem of estimating treatment's effect under the simplest case of a single treatment and outcome, and subsequently generalize it to our setting of interventions and of one or more treatments and multiple outcomes. So under a single treatment and outcome, we consider n independent random variables from a distribution. So you have do we have to say anything here? No. Well, okay, we can go just to what the triplets are in these variables. So you have your outcome yi, your like description of the patient xi, and your treatment, which is 0 or 1. And they say we use the Neumann-Rubin potential outcome framework, which is that so you have two different treatments. I mean, two different outcomes. One is if the treatment is given, and one is if the treatment isn't given. And that's what these two things are describing. Yeah. I think this is just a notation thing. I was like, why are they introducing this? But I can understand why they are introducing it, because what they're saying, for example, is they want to know what's the difference in outcome if the treatment is given versus not given. And here they're introducing the average treatment effect, which is where they're taking the integral to get the expected value of the difference in outcome over the entire population, P. And over here, actually, they're showing you like the outcome of a patient is always going to be one of the two of these things. So they're mutually exclusive. You're either going to see Y1 for an individual I or Y0. That's the key point of why they have this notation here. And then the conditional average treatment effect is when you're conditioning on the on the individual, like you know the individual's description and you want to know what the estimated treatment effect is by performing, like taking the expectation over all other uncertainty in the problem. Yeah. And that average treatment effect estimate is tau of x. And that's what this problem is about. And that's why it's can be applied to at the individual level, because it's conditioned on the description of the individual versus averaging over the entire population. And they make some, this is the next set of fundamental assumptions or things to learn from this paper, I think, if you want to get into causal inference, which is in order to do all of the math that they do later on to make, to get some guarantees, to make the equations work out, they make these following three assumptions, which are that the first one is that there's unconfoundedness. There's no unobserved confounders. And what this assumption is saying is that if you know the description of the individual, then knowing which treatment is performed should give you no additional information for knowing what the outcome for the individual would be if they are treated versus, if they are treated, which is Y1, versus if they're not treated. It kind of looks like when I was looking at it, it's like, oh, this seems very trivial, but I can understand what they're saying. They're basically saying there's nothing left out of the description of the individual that is actually important information for understanding what the treatment effect would be. And then the second one is consistency, which is that the outcome is the outcome based on the treatment that is given. So if a patient is given a drug, then the outcome should be the outcome that's of the patient being given the drug. Again, kind of trivial if you think about it, but it's important for the math, and it could not be the case. So for some reason, if you gave the patient the drug, maybe for some reason there's something in their system that negates the impact of the drug, and so it's as if they didn't take the drug, and the outcome would be of them not taking the drug because the drug had no impact.
Yeah, isn't the first one essentially saying there is no additional variable that could describe why a patient did get treatment, and that variable also correlates with the outcome, right? That is essentially what the first one saying. It's
So there's
That is
no
actually very, very, very non-trivial, right? So there is, say patient has blue eyes, and somehow it works better on patient with blue eyes, and the doctor tends to give it more with patients who have blue eyes, and that is not observed in the data set, right? So then suddenly the treatment and the outcomes are actually coupled, but you don't know it in your data set because you might not have blue eyes as a feature in your data set.
Mm.
And then whatever you measure for an effect can be maybe bounded, but it wouldn't be the true causal effect because you would need to know number of blue-eyed patients in your data set, I think.
Mm. Yeah, I see what you're saying. That's a very good point.
It's hard to get from the nomenclature though. It's the abbreviations. It's the consistency one. I don't quite wrap my head around what it's actually meaning.
Well, so for the first one, just so everyone understands that assumption, it's that maybe there's some variable or description of the patient that's not in X that changes the propensity to treatment, a specific treatment. So, for example, maybe the classic example is maybe someone's rich, so they have more of a propensity to get treated, and like by an expensive drug that someone who's poor isn't, and then that could have an impact on their outcome, which isn't.
Yeah, if their richness would also directly feature into Y as well, right?
Mm-hmm.
Yeah.
For consistency, like I said, my understanding is kind of the example that I gave, which is that it's saying that if a patient is given a treatment, the outcome that you observe is a sample from like the distribution over outcomes when the patient is given the treatment.
Yeah.
And so but it might be the case that there's something that stops the outcome distribution for that patient from being that of the treatment, even though they were given the treatment. I'm sure if we had someone who was an expert in this, they would be able to give us a good example. And the last assumption that they make everywhere is overlap, that treatment assignment is non-deterministic, such that for all X in the support of X, so for every individual, the probability of a treatment, of being treated, is non-zero, but less than 1. Also, not for sure. So that means that there's always going to be a non-zero probability that the patient is treated or not treated. Okay. And so they say, okay, now let's extend this, first of all, to a multidimensional outcome, which is you might have multiple impacts that you're trying to estimate for. Although again, in experiments, they only, I think, look at one. Let's see. No, maybe for the cell. No, I think for both of the experiments, they're only looking at a single outcome. So I actually don't know what's the importance of estimating multiple outcomes. Like, why do they introduce it? Maybe just to show that the problem can be formulated that way. So it's a multidimensional outcome. So instead of being a single real number, you have a vector of real numbers indicating the outcome of measuring like multiple impacts that the intervention could have. And then also you have multiple different treatments. So instead of having a single 0 or 1 indicating the treatment, you could have T different treatments. For example, maybe you administer multiple drugs at once.
I think the multiple outcomes might be useful for side effects, right? So where one Y could be a treatment effect that say does it cure cancer, or on the second one might be does it raise your risk of heart attack, or will you have a heart attack, right? So which does make sense to have a look at both of them sometimes.
Oh yeah, I totally agree with that. I guess my comment again was, and then is it maybe it would have been stronger if one of their experiments was trying to estimate multiple outcomes.
Yeah.
But again, it's quite hard to do to like cover the full base of experiments that you might want to cover for a paper. And so yeah, they just extend it so Y can be multiple multiple y can be a vector instead of a scalar, and then that w can be a lot more, many more outcomes, 2 to the t outcomes. And they have to make, the main assumption that they have to make still is that the overlap assumption, which is that any of the 2 to the t treatments, so any combination of drugs might be administered to the patient. There's a non-zero probability of that happening. And then let's see, is there any other assumption they make? No, I don't think so. Just so everyone knows, the reason why they make these assumptions is so that the conditional average treatment effect is identifiable. So there's certain assumptions you have to make, which if you don't make them, then it's not possible to actually calculate the conditional average treatment effect. And these assumptions are required in order for the math to work out that you can. And for this problem setting, like we said before, they separate their training and validation set from their test set based on seen interventions and unseen interventions. So seen interventions are ones that are seen during training and validation, and unseen interventions are ones that are not seen in training and validation. Okay, yeah, they're just introducing problem one. Okay. And they make a distinction between like just zero shot learning and their method, their problem, in the sense that usually in the zero shot case you have like for example, I'll just use ImageNet as an example of the zero shot case that they're saying is different from theirs. So in the normal zero shot supervised learning case, you have like maybe ImageNet has 1,000 classes. You train on 900 of them, and then you see how good it is at classifying the other 100. So that's kind of like the zero shot setting where you have unseen classes. But here, you actually have unseen treatments. So actually, a component of the input to your model is unseen, and it never sees those. It's hoping for shared structure that allows it to correctly between those interventions and the ones that you train on to help you learn to effectively estimate the treatment of those interventions. Yep. Okay, so let's go through this. There's 3 methods to their like 3 components to their proposed model. One is the metadata set. So what they do is they have like this massive data set of different interventions, and they create like sub data sets for each intervention, where you have like examples of patients who are treated with that intervention and examples of patients that are not treated with that intervention. I was wondering if they share examples of not treatment between data sets, because like a patient that's not treated with any drug could be used in any of these data sets, for example. And whether they're using, if they use, could you use, actually I think WI equals 0 is just, did not receive any intervention. So yeah, whether they're sharing between data sets for untreated patients or not. But so you, instead of having one data set D, you have J data sets, for one for each intervention. And if you remember at the beginning, I was talking about the naive approach. The naive approach could be to just use D instead of separating it into J smaller data sets. So that's the first thing that they do, and then it relates to their meta model training method. So let's talk about that before we go into their estimating of pseudo outcomes. So the way that they train their model is that they train the model on all of these different data sets in series. They randomly They randomly order the data sets and then they go through them. Oh, actually, they don't even randomly order them. They just sample them. So they sample one of the data sets. They get task data for it. And they say that they have to subsample the task data because, surprisingly enough, they have so much data for each of these tasks that they don't want to have like way too much data for each task. So they subsample, and that's how they get this data. We'll get back to the pseudo outcomes later. And then they train on that specific task, and then they update the model. So again, that's a key difference between the naive approach and this one, which is that you're training the model only on a subset of the data based on it being for a single intervention, and you do that over and over again, instead of just taking the data for all the interventions and mixing it together and feeding it to the model that way. And then the second thing that they do is they use this meta-learning framework called ADAPT, which is reptile meta-learning. And again, they claim that their method can be used with any meta-learning framework. I'm like, well, if you're in your method, you're literally using you're using a single meta-learning framework. So I can understand why it would work with any meta-learning framework, but again, yeah. Anyway, and I think the paper is really interesting even without making those claims. So maybe that's where I'm coming from with some of that. Like, okay, you're saying it can be used with any causal learning model and any meta-learning framework, but you get great results and you're using a specific one. So maybe you don't have to do that. But I actually think the meta-learning framework that they use is very interesting. So, and like, okay, let's talk about possibly the naive meta-learning framework which you could use versus the one that they're using. So the meta-learning framework, the first step is you get a sub data set, an intervention data set, and you train the model on that. And the naive approach would be that you just train it as if it's its own, as if it's the data set that you're training the model on. And so what you do is you sample a batch, you calculate your loss, you update the model, and you do that until you've gone through the entire intervention data set. And then you sample the next task and you train the model on that one. That's what I would call the naive approach. But actually what they're doing here is they take the model, they sample an intervention data set, they take the model, they copy the weights, they train that model on the intervention data set. Wait, sorry, I'm just gonna add someone that just joined. So you sample an intervention data set, you take the model, you copy the weights, you train it on this intervention data set, and then you get the weights from the intervention data set. And that's what this is showing here. You get the weights so you get the finally trained model from that intervention data set, you get the weights from that, and you calculate the difference between the two. And you view that as your gradient. And then you make a small step in that direction. And then you go on to the next task. So here, basically what they're doing is instead of just using the models from the weights from training on that data set, they're making a small step in the direction towards those weights. So I think that's a way maybe of like not over biasing the model as you're training it on these multiple different tasks, so that you don't either to facilitate exploration or maybe even just to like make sure that you're going in more of like a direction that is good for all of the tasks over multiple iterations. I hope that made sense. But so that's one of the key ideas here. They're not actually using a gradient based. They're estimating the gradient. They're using the reptile gradient, which is just the difference between the original weights before training on that data set and the weights after training on that data set, and they're using that to update the model. So two components of the method that we've talked about are making these intervention data sets and training the model on those individually instead of looking at all the data at once. And then second of all, this special method for updating the weights of the model where you're using like an estimated gradient instead of an actual gradient to estimate them between data sets. And then the last, and these two elements are meta-learning elements, the paper. The last element is estimating pseudo outcomes. So they're not actually using the outcome for each patient as the training, as the target or the label that they're calculating the loss with respect to. Unfortunately, there's an entire other paper, this one here, which actually I'll just post in the chats in case anyone is interested, where they, oh wait, how do I get to the chat? There we go. Here's the paper. Where they describe the entire method for estimating pseudo outcomes, but the point is that if you use just the treatment of the individual as the label, then you're going to get, I think, a biased estimate of the true expected treatment effect or average treatment effect. So I looked a little bit into the paper, and I hope this is a good explanation of this other paper where they estimate pseudo outcomes. Essentially what they're doing is they're parametrizing either the average treatment effect or the estimated treatment effect using some simple model. And they're using the difference, but they're using those parameters to calculate an unbiased estimate. So what they say is the pseudo outcomes are unbiased but noisy estimates of conditional average treatment effect. So they probably like have high variance, but they're unbiased. And that's what they're using instead of using the actual treatment effect that was recorded for that individual. And so there's another, that's a third part of the method, and that's from the causal learning methodology, from causal learning literature. And again, this is like the third part that separates from the naive approach. They're not actually using the labels of the data set of each data point. They're using like a modification to the label essentially to train the model. So I would have liked to see. Oh well, they do check how important that is for in their ablation study. But so yeah, those are the two. Those are how they differ from the naive approach that we had talked about in the beginning. Then they have a theoretical analysis where they basically they make some additional assumptions, like that the meta-learning framework only trains on the sampled task for one iteration, and they create a bound for like how much error there is between the learned model and the optimal model. If anyone's interested in the math, it looks interesting, but I didn't think it was super important because I personally am more interested in empirical results because I think they tend to generalize better than like theoretical results do, funny enough. But yeah, they're basically giving a bound on like how wrong the model can be with their method with respect to like the optimal model in terms of the loss that they're training on. Okay, let's talk about experiments. So they evaluate their model on two data sets. One is health insurance claims, predicting the effect of a drug on a patient, and one is predicting the effect of a perturbation on a cell. So for the health insurance claims, there's two drugs that are included in these health insurance claims, and there's one side effect of these drugs which is potentially fatal, which is the effect they're trying to estimate. Like there's this what would I call it? Pathology maybe is the right word. Or this symptom, disease, whatever, that can happen from taking one of these two drugs, and it happens in like 10 to 20% of, oh no, it happens very rarely in patients, but it has like a 10 to 20% mortality rate. And so they're trying to estimate the impact of these drugs on having this symptom. And then for the second one, they're perturbing cell walls, of perturbations of a cell or cells, and they're trying to estimate the effect on expression of landmark genes. Let's go over here to see what it says. We don't look at all. yeah, I guess it's trying to say like what's the impact on the gene. So actually, this is a multi-class classification problem. I mean, it's a multi-outcome classification problem. One cool thing I just wanted to highlight about the second data set, in case you're interested in doing causal learning research, is that for the second data set, they can have replicas of the same cell, so they can actually estimate average treatment effect on a specific cell, which I thought was really cool, because they can take the cell and perform the treatment, or take the cell and not perform the treatment, and then and probably as many times as they wanted, but if they could just do it once, and they'd have like an estimate of average treatment effect. So in a way, I was like, is this a causal learning problem? But at the same time, I was like, great data sets to do experiments on, because you don't have to. You'll see with the other data set, they have to do some pretty complex calculations to estimate to evaluate their model. So actually, let's talk about the second data set first. And then we'll talk about the first, because we don't have that much time left. But so for the second data set, you have a description of the cell, which is cancer cell. Is from the Cancer Cell Encyclopedia. The outcome is the expression of landmark genes, and the intervention is introducing one of many kinds of molecules to the cell, perturbigin. And they describe it by using this RD kit, molecule embedding, this RD kit, which is probably some model for doing molecule embeddings. And if we look at the results, they compare their model to 3 different models: S-Learner, Graphite, and SYN. And let me just check something. I want to go to the baselines. Oh yeah, okay. These are all like 0-shot methods. And so over here, just so you can understand the results, and I want to focus mainly on the ablation study. So they take like the 50 most impacted genes, and the mean squared error that they have is 3.78 across the data set for the 50 genes, and for the 20 genes, it's 4.11. And so this is like a good benchmark for you to measure against. Anyway, and they do an ablation study where they show their method without the pseudo targets, so the ones that they calculate, that's without RA-Learner, and then they have it without meta-learning. Interestingly, without meta-learning, the results are almost very comparable, in my opinion. So they're very similar, but without the pseudo outcomes, then they're much worse. So it seems like using those targets are very important for the performance of this model, using these calculated targets. I actually thought that was a really interesting result, because how often do you hear about how often do you hear about methods, or do you know of any methods that are where we're literally changing the label to make it more accurate at estimating unseen labels, like the labels in the training set to make it more accurate at estimating labels in the test set? So I thought that was pretty cool. And then they outperform all of these baselines, which are previous methods that do conditional average treatment effect estimation. And I think it's 0-shot as well for these ones. Yeah. Let me see. We have some time, and then just to summarize the results on the other data set, which is for estimating the possibility of experiencing this this deadly symptom or disease from taking these 2 drugs. There's a couple of different results. The main one that's really interesting is that they took methods that need to have data of the intervention being implemented on an individual to estimate average treatment effects. So they're not doing 0-shot. They're actually needing to take they need data to train the models. And the method here outperforms all of them on estimating average treatment effect. And it also outperforms the baselines that could also perform zero shot as well. So overall, it's really good. The only thing that's hard here is like these metrics. I was looking into them, and they're pretty in like we can talk about it if you want. I'm not going to talk about it, so I can leave some time for. I'm happy to talk about it though, because I did spend like a good 15 minutes looking at the equation for this metric. But because you can't estimate average treatment effect, because you can't see what it was like if the patient got the drug versus not, they have to do a whole set of calculations just to calculate what they consider to be a good metric for evaluating their method, which is quite involved. The basis of it is that you take like the top N% of performing models based on your model versus the entire data set or the entire test set, and you compare their performance, and you do it by essentially training another model and seeing the difference in performance. But that's a poor explanation of it. I can go into more detail, but it is quite involved. So I think it would be more of something that I would encourage you to look at yourselves. If you're curious about how they're calculating these metrics on the first data set, for the first data set, it's over, it's this equation here, essentially. Yeah. So to summarize the paper, I feel like I hope there's some, oh yeah. Oh, this one has similar metrics explained. Thanks for the result. I mean the reference, Arvid. So to summarize the paper is looking into zero-shot causal learning, which means that you're looking into estimating the impact of an intervention when you have no data on it. It's focused a lot on biology, and in this case, like the impact on someone's health or on cells in terms of results. I think it's a really cool paper. It has good results and some interesting methodology. I guess, like I said, I would have liked to see without both of them, like what would actually, it shouldn't matter. Okay, yeah. So this is the method. Hope you guys like the paper. I wish I gave you a better explanation of everything, but there was a lot to cover, and I didn't have a huge amount of time. I do like causal learning, so I'll try to do a better explanation on the next paper that I do on causal learning. But does anyone have any questions or anything they want to talk about?
I wonder how one would extend this to say drug research. Say, I would almost think that you can put on top of that something like an exploitation bias in like put one more meta level on it to sort of guide for new drugs. That would be kind of interesting, I would think.
You reminded me of here that I'll just post this paper here. There's a paper that actually does that. It's called Gene Disco. And it's about experimental design of drug discovery and how you can optimize it. So I just posted it. But yeah, it would be cool to use this method. I actually, as my follow-up to this was, I really want to look into these recalculated targets that they're using to train the model, these pseudo outcomes, because like I said, it's a concept that's very new to me, this idea of using different labels, like modifying your labels during training to make them more accurate during test time.
Yeah. Also, one thing I wondered whether the treatments themselves are probably not independent, meaning that say regional variations might say the patients come from different countries, so that they might have different X distribution or centers, right? But also the treatments then might be correlated with that. And I don't know, did they actually mention anything about that as an assumption that those have to be independent or not? Because I would almost think that this would also be yet another confounder on that problem.
Let's look at the description of the data set. Oh, it's all in the United States.
Yeah.
So,
But I mean, it's more like on a hypothetical question. Would it matter if they are correlated? And I would almost think it probably is, because the model would not be able to tell whether something is based on the treatment feature or based on a patient feature, right? If they were too dissimilar. Of course, under the assumption that there are no yet other hidden confounders between those that are not observed.
yeah.
But,
It is like a really hard problem, but I think it's kind of a fundamental problem with causal learning, that it's really hard to say, I really don't have any hidden confounders. You probably do, but I guess you hope that their impact isn't that great. Or I do know there's a lot of literature around like marginalizing out the impact of hidden confounders.
Yeah, even worse is if you have there's certain variables you don't want to have in a data set because they actually make it worse. It's because they are confounding on the treatment you kind of get, and those it's a whole kind of worm. So it's actually really, really cool, because you actually have to think about the data, which is nice.
Yeah. Oh, I do have one more comment about this paper. I really hope that I did not submit it to ICML, because it's a really recent paper, and in theory, ICML is a double-blind review process. And I'm just saying this because I've seen it a ton of times before. So if you publish on arXiv the same paper with your names on it, then it's no longer double-blind review. So I really hope that they did not submit this to ICML, or for that matter, if they're going to submit it to any double-blind review process, because they shouldn't publish it before the results of the review are coming out. But anyway, that's just kind of like a chip on my shoulder thing, that I'm like, if you're submitting to that type of conference, you shouldn't be publishing the paper outside of it until you get the results back. Anyway, thanks everyone for joining. I'm gonna stop the recording now.